All right. So Kim just had a question about the mole. Let's talk a little bit about the mole. When we let's do that. Avogadro Avogadro realized that different atoms have different relative masses. So here is, and I apologize. Oh, no, that's the right way. I love it. Here's the periodic chart. This is the periodic chart I used to give my students every exam that they had because I never believed in memorizing the periodic chart. The only teachers who insist that students memorize this are the teachers who don't understand that there's too much about chemistry. There's no time for trivialities like memorizing the periodic chart. If you did memorize it, and if for some bizarre, strange reason, 10 years down the road, you needed some number from it, even if you remembered it, you wouldn't trust your memory. You'd go and look it up somewhere, and they're available pretty much everywhere. So I never saw the point of memorizing. Let's use one of my favorite examples. So over here, you have chlorine. And last time we talked about atomic number, which the atomic number of chlorine is 17. Now, if the atomic number is 17, how many protons does it have? Do you remember?
$17.
The atomic number is the number of protons. The two-letter symbol is Cl, and notice that the atomic weight, using the old-fashioned nomenclature these days, and more appropriately, it should be called the atomic mass, is 35.45. Now, last time we talked a little bit about the numbers down here, like californium, where you're going to see a whole number. For californium, the number is 251. That 251, since californium is an unstable isotope, an unstable element, that is the atomic number, the atomic mass number, not to be confused with atomic mass. It is the atomic mass number of the most stable isotope. And that means that if you want to know how many neutrons it still has 98 protons. So the number of neutrons, take the atomic mass number minus 98, which is the atomic number, well, 93, is that right? Did I do that right? I don't know, I did that right. My math skills have atrophied, and that is not a good thing. That's not right. Ooh, I did it right, 193. So there are 193 neutrons. Now, the only thing that the neutron has anything to do with is the isotope, which, like I say, is kind of beyond the scope of this course. But the number of neutrons help are related to nucleus stability. That's why some isotopes of uranium or plutonium are explosive and some are not. You know, you can use a very specific isotope of uranium, plutonium. A very specific isotope will give off an atomic explosion. Just one isotope, which means the only difference is the number of neutrons. But it's very hard to isolate it because chemically they are almost identical. So how do you explain then that chlorine is 35.45, roughly 35.5? About 35.5 grams per mole. By the way, those numbers, periodic chart, periodic weights, always add the units gram per mole. Gram per mole. If you want to use them in factor label method, you must have units, and the units for those atomic masses are gram per mole. But how do you get 35.5 grams per mole? Because there's no such thing as half a neutron. So how do you do that? Well, I mentioned briefly last time, I didn't go over it. The 35.5 is the average. It's actually the weighted average atomic weight of all naturally occurring chlorine. Okay? So there are really two isotopes of chlorine that occur. In great abundance. There are actually others, but these are the two in great abundance. And when you isolate chlorine, you're going to get a mixture of chlorine 35, chlorine 36, and all of the other chlorines that you have. Remember that this is the atomic mass number up here. So this is the isotope. The isotopes are called chlorine 35 and chlorine 36. And they occur in roughly 50-50 ratio. Actually get slightly more chlorine 35, which is why it's slightly less than 35.5. But it's about 50-50. So you take the average of 35 and 36 and you get 35.5. All right. So that's why. And when I say weighted average, now if we go back to the periodic chart, go back to the periodic chart and take all this schmutz out that I did. My eraser does not always want to erase. I wonder what is up with that. I don't want all that there in the future. So if we look at, say, the top row, boron, carbon, nitrogen, oxygen, well, if you look here, it's silicon. You'll see silicon is slightly over 28.09, so over 28. So you're going to get silicon 28. You're probably going to get silicon 29. I'd have to look it up to make sure I have the exact right isotopes. But it's going to be 90% silicon 28 and only 10% silicon 29. So the weighted average is only slightly above 28 because you have so much more of one than the other. That's what I mean when I say the weighted average. Avogadro realized let's look at carbon and oxygen. Carbon has atomic weight of roughly 12. Oxygen has an atomic weight of 16. All right. We go back to our notes and we notice that. And we want to look at, and it started off, by the way, with masses. We want to look at the ratio of carbon to oxygen. Chemists realized early on that 12.01 grams of carbon would always mix with 32.00 grams of oxygen. But Avogadro realized that the relative masses of these elements are always the same. So it was Avogadro who realized that if you have 12 grams of carbon and 16 grams of oxygen, you have the same number. 12 grams of carbon and 16 grams of oxygen will have the same number of atoms because the relative weight, oxygen is just a little bit heavier, is always just a little bit heavier than oxygen. If the average, and I'm pulling these numbers out of the air, so I'm probably wrong. The average weight of a man is 180 pounds. And the average weight of a woman is, say, 150 pounds. I honestly have no idea what the average is. Then you can figure out the ratio of men to women based on weight. So if you had 1,800 pounds of men and 1,500 pounds of women, you have the same ratio of men to women. Well, basically, you'd have 10 men and 10 women. Because the relative weights, the average weights, are kind of fixed. So if you have 12 grams of carbon and 16 grams of oxygen, you have the same number of carbon and oxygen. Avogadro did not know what this number was, so he called it a mole because a small blind animal walked into his lab and bit him in the toe. He called it a mole. He didn't know what that number was. He honestly didn't know what the number was, but he figured out that the ratios of the elements are always fixed. So if we have 12 grams of carbon and 32 grams of oxygen, what's the ratio of carbon to oxygen? Now, I intentionally chose 12 grams so we would have one carbon. How many oxygens would we have? What's 32 divided by 16? 2. 2, exactly. I think I heard you say 2.
2, I did.
So with 12 grams of carbon and 32 grams of oxygen, we have twice as many oxygen as we have carbon. And we have our compound, CO2. Now here's why this is important. Conceptually, when we think about. It is much easier to think in terms of atoms. It is easier to say 2 oxygens for every 1 carbon. It's just easier to say that. 2 oxygens for every 1 carbon. If Avogadro had not come up with this concept of relative masses, we would say 32 grams of oxygen to 12 grams of carbon, and it becomes much more confusing. It's much less, doesn't make a lot of sense to us. So in our minds, we prefer to think in terms of numbers. And by the way, we don't actually say 2 atoms of carbon, 2 atoms of oxygen for 1 atom of carbon. We say 2 moles of oxygen for 1 mole of carbon. We could just as easily say 2 dozen oxygen for 1 dozen carbon. We can use any number we want in there. 2 scores of oxygen to 1 score of carbon. A score is 20. 4 score and 7 years ago is 87 years. So we say mole. And the reason we say mole is because in the lab, when we're actually doing these experiments, we cannot, there's no device that measures the number of atoms. There's no instrument that measures moles. But we do have an instrument that measures mass. So we can measure grams. We cannot measure moles. See what I mean? So we think in terms of moles, but we're forced to work in terms of mass. This is what atomic masses give us. If we have a compound and we do an analysis on it, and it's 72 grams of carbon, 12 grams of hydrogen, and 96 grams of oxygen. And we can find this. We can figure this out. That doesn't tell us anything about what we actually have. So if we give ourselves a little more room here, move this down, move this down. But we know the carbon, 1 mole of carbon is 12 grams. We know that 1 mole of hydrogen is 1 gram. And we know that 1 mole, and all these numbers, they are all coming straight off the periodic chart. In your book, on the inside cover, you have the periodic chart. So if you look these up, you will see carbon is 12, rounding here. Carbon is 12, hydrogen is 1, oxygen is 16. This is very, very wrong. 12 moles. Notice I'm just using the factor label. We've not talked about how to do these calculations. We don't have to. This factor label takes care of it for us. Now we know that our compound is C6H12O6. This is in your gummy bears. This is just sugar. So in the lab, we can figure out the grams. But conceptually, we want to know the moles because it gives us that ratio. 6 moles of carbon to 12 moles of hydrogen to 6 moles of oxygen. That's what Avogadro's number is. And we actually gave the number 6.02 times 10 to the 23rd. We did that when we were covering sig figs. I'm sorry, scientific notation. Does that answer your question at all, or did I just confuse things for you?
It's a little confusing, but that's okay.
Where did I lose you?
No, you didn't. It's just, I'm just trying to absorb it all.
Yeah. We're not going to do, I don't think, a whole lot of calculations like this. And if we do, you'll see it again. But this is kind of an introduction to the mole and atomic number and all, atomic mass, not atomic number, but atomic mass.
Okay.
Always grams per mole. So last time we started talking about the atom. And we came up with a model, Rutherford's atom. Said you had a nucleus in the center. The nucleus contains the protons and the neutrons. And like I say, the only thing that the neutrons really do for us is it's related to the stability of the nucleus. You have the right number of neutrons, you have a stable nucleus. You have the wrong number of neutrons, it's very unstable. Electrons are somewhere around outside of the nucleus, but so far we really don't know what the electrons are doing. Well, when we talk about physics, usually we think in terms of Newtonian or classic physics. Now, Newtonian physics assumes, and we're going to go into more details probably on Thursday, but it assumes that we know everything we want to know about a system. Newtonian physics assumes that we can measure position which we'll denote as an x, and velocity, let's call it velocity. For some reason, physicists love combining mass and velocity. Mass times velocity is called momentum. And momentum is always better than less momentum. We're going to denote velocity as a V with this funny little arrow on top of it. The arrow denotes a vector. Vector means we know both magnitude and direction. So if I were driving to Sioux Falls, I would know I'm driving 70 miles per hour due north. If all I gave was my speed, I'm going to Sioux Falls and it's 70 miles per hour. Well, if I didn't say due north, maybe my sense of direction, maybe I'm heading west because I'm kind of a directional idiot. So if we know position and velocity exactly, then we have Newtonian physics. The problem with Newtonian physics is there are certain phenomena, observable phenomena, that cannot be explained using classical physics. God bless you.
Thank you.
For example, Newtonian physics fails when we talk about black body radiation. If you look at your pen you look at your stylus, you can see, actually, this is a bad example because it's black. If you look at my degrees back here, you can see my degrees because ambient light is coming in mostly from the window, reflecting off of that and going back into the camera. All right. Black body radiation, if you take, for example, it's light that comes from inside the material. Your screen right now is an example of black body radiation. There is not light illuminating it from an external source. That light is coming from inside the house. Get out of the house. It's coming from inside the house. Sorry. Okay, it's Halloween season. It's coming from inside the screen. Classical physics cannot explain that. Someone named Niels Bohr, well, actually, a lot of physicists did that. So if you take a tube and fill it with some kind of a noble gas, and run electricity through it, it will glow with a very specific color. This is black body radiation. This is something that physicists could not explain. Run this through a lens system, which I always denote like this, to get a nice narrow beam of light. And then run it through a monochromator. A monochromator will separate out the various colors of light into their individual colors. This is sometimes called a prism. And they notice that these colors of light have very specific wavelengths. It's not continuous. It's not a continuous wavelength. It's very specific wavelengths where you can have this wavelength here or this wavelength here, but nowhere in between. They are very specific wavelengths. And the wavelength is related to color. The wavelength is related to color. Now we can learn more about this, because as it turns out, the wavelength frequency. The wavelength times the frequency is equal to the speed of light, which is a constant, 3 times 10 to the 8th meters per second. So frequency means if you put a pen up, actually think about it, the ocean waves. If we were sitting on the dock in the bay, letting the time pass away, just sitting on the dock at the bay, wasting time, we might watch the ocean waves come and crash over some fixed object like a rock. Very soothing sound. It's exciting to see the waves crash into the rock. The frequency is how many waves crash into that rock per second. Per second is called hertz. That's your frequency. How many waves crash at that fixed point per second? Speed of light. We're always going to have 3 times, well, okay. So anyway, I'm kind of confusing things here. So anyway, that's what frequency is. How many will strike a fixed point per second? You put out a solar panel, how many wavelengths of light will strike that per second? That's the frequency. As it turns out, and I want to put this on the same page, so I'm going to go back and it's going to get a little bit confusing. As it turns out, the frequency times a constant called Planck's constant gives you the energy. Planck's constant, if I'm remembering, is somewhere around the range of 6.26 times 10 to the negative 34th. It's a well-known constant. It's Planck's constant. If you take these two equations and combine them, what this is telling us is that each one of these colors is a very specific energy. This is something that cannot happen according to Newtonian physics. These are discrete energy levels. They're discrete energy levels. Those electrons are jumping around and giving us this much energy or this much energy, but nowhere in between. It is impossible to have this much energy. It's either this or this, nothing else. That's impossible. When you get in your car and drive to work, you don't go from 20 miles an hour to 60 miles an hour without hitting anything in between. It's impossible. It's continuous. For us, it's continuous. It's not discrete because we have to drive every speed to get up to that speed we want to be going. Electrons are these light. They just don't do that. We say the energy levels are quantized. They are discrete or quantized. Niels Bohr came to realize that these energy levels will follow an equation like this. This is a symbol of proportionality. I'm really confusing things. You can turn a proportionality into a constant. You have to figure out what that constant is. But basically, there is some random constant here, and it's actually not random. I'm not giving it to you because I'm not 100% on the formula, but it's something like this. It's something like this. Should be the Rydberg constant. The Rydberg. But I think there may be other components in there as well, which is why I'm resisting trying to write it exactly. where N1 and N2 are integers. Integers. Starting at 1, there's some kind of an integer, 1, 2, 3, 4, 5, 6, 7, blah, 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 whatever it is. So you can actually match the exact energy by figuring out what those integers are. He called those shell numbers. So if the electron is jumping from shell number 3 to shell number 2, you get a very specific energy. Just like here, we had a very specific energy. So these shells have very discrete, very specific energies. That led him to believe that the way the atom works, the Bohr atom, you still have your nucleus in the middle, but now you have discrete energy levels. And the electrons live in these discrete energy levels. So they have very specific energy. Very specific energy. It is 10:38. Let's come back at 10:45. Let's take a quick break. We will return at not 10:45, it's 10:40. So let's return at 10:45. Let's take a 5-minute break and we'll talk about the ramifications of these discrete energy levels when we return. Is that fair?
That's good.
Do you have any questions before we break?
Nope.
All right. See you in 5 minutes. All right. Welcome back. So, what we've discovered so far, and I know that we're getting into a lot of detail here. We're about, I'm not going to say that. Scientists like Madame Curie, and she wasn't the only one, gave us the 3 subatomic particles, the protons, the neutrons, the electrons. Rutherford showed us the existence of the nucleus, which contains the protons and the neutrons, and he's the one who said that most of the space around the atom is occupied by the electrons that are not in the nucleus. Now Niels Bohr has given us the concept that there are discrete energy levels, and of course this is not his only experiment. He's not the only one who did it. But now we know there are discrete energy levels around the atom. So let's look, for example, at sodium. Sodium is atomic number 11, which means it has 11 what? That's right, protons. And if it's a neutral atom, pardon my voice, puberty, you know, if it's a neutral atom, it also has 11 electrons. We're going to talk about that actually here before the end of the day, if I can stay on schedule. As it turns out, there are 3 what we call ground state energy levels. 2 of them two of these electrons live in the first ground state energy level. Six live in the second. So we have 10 electrons so far. One of these electrons lives in the outermost energy level. Before we go any further, I want you to notice that the only electron that interacts with other atoms is the outermost shell. There are 3 shells. Only the electrons in the outermost shell interacts. All right, well, we call this ground state. We'll talk about that in a second. Ground state simply means lowest possible energy. While we're on it, the excited state is anything other than the ground state. If it is not ground state, it is excited state. If ground state is the lowest possible energy, then excited state must be higher energy than the ground state. Excited state, higher energy. Now, here's a very important concept. The outermost electron The outermost electrons are in what we call the valence shell. The valence shell is the outermost shell of the atom. All of the rest of them are inner shell electrons. When atoms interact, the inner shell electrons do nothing but support. They basically give the support for the valence shell electrons, for the outermost electrons. So those inner shell electrons actually don't interact either. The nucleus, and in the example of sodium, those 10 electrons, there are 2 inner shells in sodium. We're going to talk about how you can tell how many there are, how many shells. We're going to talk about all of that in a bit, probably Thursday. But those inner shell electrons do nothing but provide the structure for the valence shell electron. In the valence shell, that's the electron, or those are the electrons that are actually interacting. Okay? That's all chemistry is. Interaction of valence shell electrons. Now, as I said, there are excited state shells. So there are higher energy shells. It's just that at the ground state, they're not occupied. Okay? The ground state, they're simply not occupied. So here's what's causing light. Here's what's causing black body radiation. If you input some form of energy into this atom, heat, laser light, something, if you input energy into this atom, it's going to cause this valence shell electron to jump from the ground shell. It's going to absorb that energy to a higher energy shell, to an excited state. So it's going to go from the ground state to an excited state. Now, the law of conservation of energy says if it absorbs energy in jumping to a higher shell, it will release energy when it jumps down to a lower shell. So it's going to live only fleetingly in this higher energy. When that electron drops back down to a lower energy shell, let's say it jumps down to this shell instead, it's going to give off light. So as it goes from the excited state, notice it doesn't have to go all the way down to the ground state again. It can go from higher excited state to a lower energy level excited state. And when it drops, it doesn't matter if it goes all the way back to the ground state or if it goes to just a lower excited state. When it drops from that shell to a lower energy shell, that energy has to be conserved. That energy has to go somewhere. And where it goes is it's given off as light. This is spectroscopy. Notice that light we usually write as h nu. As you recall earlier, energy is equal to h nu. So when we write h nu, what we're talking about is a very specific energy, because these energy shells have very specific values. And when it jumps down to another one, it's going to give off a very specific energy light, which corresponds to a very specific wavelength, which means a very specific color. Okay, does that kind of make some sense to you?
Mm-hmm.
A little bit. So let's look at sodium. Just redrawing it here. And let's look at chlorine. Tell me what you know about sodium and chlorine. Did you ever hear of sodium and chlorine?
Yeah.
Should sound familiar, but not quite right,
Right.
because it's sodium chloride. What is sodium chloride? Sodium chloride is table salt. Well, as it turns out, chlorine has 7 electrons in the outer valence shell. Sodium has 1. Now, it turns out electrons like living together. No electron likes being alone. Every electron wants to live with another electron. It's all kinky and stuff. So in chlorine, most of the electrons can live in pairs. Here, here, here we call these lone pair electrons. A lone pair of electrons are 2 electrons in the valence shell. Lone pair, 2 electrons in the valence shell. And we call it that because they're happy. If they're happy, they're stable. They're not going to break up. Well, you know, there are always exceptions. They're not going to break up. They're not going to do anything. They're lone pair electrons. They're just occupying space. They're happy living their lives. Leave us alone. No, thank you. We're happy. But it has 1 unpaired electron. Just like sodium has 1 unpaired electron. Unpaired electrons, any element that has an unpaired electron is called a free radical. A free radical, unpaired electron. Free radicals are highly, highly, highly reactive. They're excessively reactive. They're very unstable because they're very unhappy. They have an unpaired electron. Who wants to live? It's not worth living alone. Well, we can take care of that, can't we? We have an unpaired electron on the sodium and an unpaired electron on the chlorine. Couldn't we just pair them up? Doesn't that make sense? Just pair them up. Let's take this electron and give it to chlorine. Now, here's something that always, always, always confuses students. We are transferring one electron, okay? Sodium is losing one electron. But the charge of an electron is negative. So in essence, sodium is losing a negative charge. And if it loses a negative charge, what will the charge of the sodium left behind be? If it's losing an electron, if it's losing a negative charge, the sodium will end up with a positive charge because it lost a negative charge. When you transfer an electron, when you lose an electron, you're losing a negative charge and you're left with a charged atom. And this is what I said before. We don't identify atoms by the number of electrons because the number of electrons can change. Number of protons remains the same. So we still have the 2 electrons in the first shell. We still have all of the electrons in this second shell as well. But now we've lost this electron in the outer shell, in the valence shell. We've lost that. So if sodium becomes a positive charge, what charge does chlorine become when it gains an electron?
Negative.
Negative. Exactly. This is a critical concept. Electrons must come from somewhere and they must go to somewhere. The world is electrically neutral. The world is electrically neutral. So you can't just take electrons and just have them disappear. You can't just take electrons and have them appear. You don't suddenly go from chlorine to chlorine negative unless it picks up an electron, and it must pick that electron up from somewhere. Now notice that we still have in the chlorine the 2 inner shells, but now the outer shell no longer has 7 electrons because it gained 1. So the outer shell now has 8 electrons. Eight electrons. Here's something that early chemists figured out. They called them valencies. Even before they knew what electrons were, they called them valencies. And they came up with what's called the octet rule, which we will talk about again. And the octet rule basically says that with some exceptions, the outermost shell always wants 8 electrons. 2, 4, 6, 8. We'll talk about why that is in a bit. 2, 4, 6, 8. So sodium can fulfill that octet rule. Sodium can get 8 electrons in its outer shell by losing that 1 free radical electron. Okay? So if sodium loses this electron here, it's left with 8 electrons in what becomes its new valence shell. Chlorine can get 8 electrons in its valence shell by adding just one more electron. If it adds one more electrons, it also has 8 electrons in the outer shell, the octet rule. That's why sodium and chlorine, that's why sodium chloride is a 1-to-1 ratio. Sodium only has to lose 1 electron. Chlorine only has to gain 1 electron. So 1 sodium, 1 chlorine, and they're happy. Here, take this from me. Oh, sure, gladly. It's not always going to be 1-to-1, but in this case, it is. And that's why sodium chloride is NaCl. That's why the formula for sodium chloride, table salt, NaCl. By convention, do a little bit of nomenclature. The cation's name always comes first. Oops, they haven't talked about that yet. Let's back up a sec here. I'll come back to that in just a second. This sodium chloride, sodium is not sodium metal, it's sodium ion. It's a sodium ion with a positive charge. Chlorine is not chlorine gas, it's chloride. It's an ion. It has a -1 charge. Okay? As we talked about, sodium gives up an electron, chlorine gains an electron. They gain charges, the charges change. Atoms with a charge collectively are called ions. They're very common. Very common. If you have a charged atom, and you don't want to specify if it's positive or negative, you have a charged atom, they're called ions. Positively charged ions are called cations, not cations. Cations, positive charged ions. The way that I remember that, my mnemonic device is right here. The T kind of looks like a plus, doesn't it? So cations, that T looks like a plus. Oh yeah, that's a positively charged ion. We're not saying what the charge is, because as it turns out, the charge can be +1, +2, +3, all kinds of things. You can always identify the cations because they're being chased by dog ions. Negatively charged ions are called anions. Here's my mnemonic device. N, negative. N, negative. By convention, this is what I started to say before, the cation is always the first name in the name of the compound. Sodium chloride. Sodium is the cation. The anion is always the second name with the ending changed to INE. So chlorine becomes chloride. So the anion is always the second name in the compound. Okay? As it turns out, it's not always 1-to-1. So let's look, for example, at another example. Aluminium oxide. The British call it aluminium, and properly so. For a long time, we had American chemists calling it aluminum. We had British scientists calling it aluminium. I mentioned their name before, the International Union of Pure and Applied Chemistry, chemists, IUPAC, had to get involved. We go until 11:20, right?
Yep.
Yes. The IUPAC got involved and they argued, should it be aluminum like sodium, or should it be aluminium like rubidium? And the IUPAC voted and decided the proper pronunciation is aluminium. And they said to the American chemists, look, the proper pronunciation, aluminium, not aluminum. The American Chemical Society, called, ironically enough, the American Chemical Society that all chemists belong to, said, oh, you're right. Its proper pronunciation is aluminium, not aluminum. So America's premier organization, chemical organization, agreed. It's pronounced aluminium. But we're Americans, damn it. We can pronounce it any way we want. So chemists still talk about aluminum. Don't ask me why. So aluminium oxide. Which one is a cation? Aluminium or oxygen?
Aluminium.
Of course. Aluminium, or aluminum if you prefer, in order for it to fulfill its octet rule, actually has to lose not one, not two, but 3 electrons. So its charge as an ion will be +3. Oxygen has to gain not 1, but 2 electrons. Its charge will be -2. Notice that when we have any charge aside of magnitude other than 1, so for sodium, it was just plus. 1 is assumed here. Chlorine is just minus. 1 is assumed here. 1 is not the case for aluminium. It's actually +3, so we have to actually write the 3 in. And I should mention, sometimes you'll see me write it one way, sometimes you'll see me write it the other. They're both correct. Sometimes you can write 3 plus, or sometimes you can write 2 minus. It doesn't really matter if the 3 goes before or after the sign. It just, either way. Now, here's the thing. Aluminium has to lose 3 electrons, but oxygen is only willing to accept 2. So will 1 oxygen suffice for the needs of aluminium? Here's a hint. No, it won't. Because the aluminium can lose 2 electrons, but it still wants to lose that last one. So is 1 oxygen sufficient? Here's a hint. No, it's not. So now we have to have 2 oxygens. Now aluminium is happy because it can lose all 3 electrons. But now we have 1 oxygen that gained 2 electrons and 1 oxygen that only gained 1 electron. Is that going to be happy?
No.
No. We have to find some ratio of our ions so that we can transfer exactly all of the electrons so everybody is happy. Here's how you do it. Just do a cross. Just do the cross. With 2 aluminiums, it's going to lose how many electrons total? 2 times 3 says it's going to lose 6 electrons. Oxygen is going to gain 3 times 2, 6 electrons. So we have a neutral ionic compound. Al2O3. A total of 6 electrons has been transferred, but we need 2 aluminiums for every 3 oxygens. So we can transfer the exact number that we need. Does that kind of make sense to you?
Yeah.
One more real quick example. Calcium oxide. Calcium, of course, is the cation. It wants to lose 2 electrons. Oxygen is the anion. It's named second, and the ending is changed from INE to IDE. So if we do our cross here, of course, we drop the sign when we do the cross. We get Ca2O2. Now, here's the thing. We have a common denominator, don't we? What's our common denominator? 2. These are called ionic compounds because they're made up of ions. The electrons are actually transferred. Here's a little foreshadowing for you. The other way we can fulfill the octet rule is with electron sharing. When we share electrons, we form a covalent compound. So an ionic compound is made up of ions. An ionic compound is made up of ions. Covalent compounds are made up of shared electrons. In ionic compounds, when you have a common denominator, you always reduce to the lowest common denominator. So Ca2O2, while formally correct, would still be marked wrong on an exam because you left a common denominator. So always, always, always get rid of that common denominator in an ionic compound. Notice when we opened the class so many pages ago, here we go. We have a common denominator for sugar. Here's a hint. Yes, we do. So our common denominator here is 6. If we tried to reduce this, we would have CH2O. But CH2O has a common name. It is called formaldehyde.
Oh.
I dated an undertaker once. I asked her what that enchanting perfume is. She said formaldehyde. How often do you sweeten your cereal in the morning with formaldehyde?
I hope not.
No, it would kill you. And the difference is these are covalent compounds. which means the electrons are not shared. I'm sorry, are not transferred. They are shared. So in a covalent compound, you do not reduce common denominator. Those numbers, C6H12O6, they tell us something specific about how these compounds are put together. For something like sodium chloride, which is the easiest example to use here, have you ever really looked at a sodium chloride up close and personal? Have you ever actually poured out salt onto a table and looked at the individual crystals? What do they look like?
Not up close.
Do it. Especially if you have if you happen to have like a microscope in the house. Take a look. What you will find is that those crystals are cubes. They are perfect little cubes. They're not cut that way. They grow as cubes. And that's because the only thing, well, the ions, sodium and chlorine, will arrange themselves in a cubic fashion. You'll have a sodium next to a chlorine, which is next to a sodium, which is next to a chlorine, which is next to a chlorine, which is next to a sodium, which is next to a chlorine, which is next to a sodium. And it forms a cube. On the atomic level, the sodium ions and the chlorine ions form a cube in a 1-to-1 ratio. But is there any reason we need to stop at just one cube? No. We can go on. Gets a little bit messy. But we can really grow that cube bigger and bigger and bigger. Each one of those sodium chloride, each one of those table salt cubes is like a giant molecule. And how big is it? I've seen crystals that grow this big. They're huge. As long as the ratio is 1-to-1, as long as the ratio is 1-to-1, that is a fair and legitimate compound. That's why in ionic compounds, we reduce the number because we can't really say, is it 1 sodium to 1 chlorine or 10 sodiums to 10 chlorines or 1,000 sodiums to 1,000 chlorines? We can't say. It can be anything as long as the ratio is 1-to-1, which is why we always, in ionic compounds, reduce that common denominator. Does that make any sense at all?
Yeah.
Because we've reached the end of our day. I've run a little bit over. I apologize for that. Any questions?
Nope.
All right. Don't be late for your next class. Thank you very much. I will see you on Thursday.
Bye.